of Things security. So what we'll be doing in this presentation is we'll be looking at typical devices that we'd find in the Internet of Things, such as this cloud camera here, and we'll find that the security of these types of devices tends to be fairly simple. And what we'll also do is we'll have a look at how we can analyze our system using Linux Kali, and we'll even use our Mac to be able to connect to a few things. So let's do some background theory first to be able to understand what the issues are. So this is our traditional model of the internet and how we use computers. We have our computer systems typically running Windows or Mac OS. They connect to servers over the internet, and we can get storage services and so on. And traditionally what we've done is we've wired our devices directly to a local bus with inside the computer. This is obviously wasteful, and a much better method is to be able to connect them onto the internet, and then we can wirelessly connect them. So that can be done locally inside the own local wireless network, or increasingly it's over the internet, where each device can actually have an IP address which can then be mounted onto the internet. So this is what we have now. We have obviously our servers, we have our instances, and typically these instances are running Windows or Mac OS. They're typically highly secure. They have unique passwords for every single device, no default passwords on them. They typically have firewalls and intrusion detection systems, and virus scanners and so on the devices to make sure they're kept up to date and patched. They'll also typically have auto patches such as the latest Java or Flash, the latest Mac or Windows update, and they're often very well tested. They're fairly robust. So typical CPU we have here is Intel x32-bit x86 architecture, or a 64-bit x64 architecture. They're typically running very fast, 3 GHz, quad core and so on, and they have quite a lot of dynamic memory to use, and their operating system itself is typically stored on some sort of long-term storage, say a 1 TB disk. Increasingly it's an SSD device here. So they're fairly powerful type devices. Increasingly though, we're moving towards embedded systems where the operating system itself is embedded into the system. So we see smartphones, they use fairly powerful processors using typically the ARM architecture. Cortex A15 is a good example of that, used in many mobile phones, or the Qualcomm Snapdragon processor using ARM8. These will often have quad cores, 4 cores on them, running about 1.7 GHz. And they'll have a non-volatile memory where we can actually update the operating system and also the programs onto the storage system. They don't have the traditional hard disks that we would see in a desktop. But what we'll see a major growth in is these types of devices, and these are embedded operating systems. These will use fairly lightweight CPUs. The typical one is the MIPS 24K of ROM, running at 384 MHz, because this is fairly powerful in order to run a printer or a webcam or over the internet. Typically what we need is just a network connection. We need some sort of interfacing to the hardware of the device, and then we have a standard interface that we can connect to the internet. Typically they might also be fairly limited, 4K or 4 megabytes of non-volatile RAM for the operating system to be loaded onto. And then they might have some more RAM that they could use to run programs and so on. Okay, but it's this area here that's likely to see the largest growth in devices. And this is typical for our webcam or IP camera here to have this type of system. So let's take a quick look at computer architecture and see if we can understand how a computer system works. Okay, what we have is that we have a high-level language such as C++ or C# or Java, Fortran and so on. And then that is then converted into machine code that can actually run on our device. So machine code, this is our Intel machine code, and this is what our ARM machine code looks like. So this tends to be fast code. We can also convert into what's called an intermediate language. The problem with this type of code is that it's specific very much for the processor, and we can't run it on any other type of processor directly. So we'll often produce an intermediate language which can then be interpreted onto the system using some sort of platform or framework. Okay, so C# and Java are two examples where we create intermediate code which is then run actually onto the hardware. Okay, so there's the two types of languages that we have. We have high-level source code, typically goes through a compiler, produces things like object code. We then link in other object code files and we produce an executable there. The other type that we have is an interpreted language, where we take a high-level language such as Python or Ruby, ESP, PHP, JavaScript and so on, and it runs through an interpreter while the machine is running, and then that interpreter then converts it in real time into a running process and onto the system. We can also call in DLLs when we're running our program, so we don't have to link in all our code. We can have a DLL which is called up when it's actually run. Okay, so that's the difference between compiled code and interpreted code. The two main types of architectures that we often see inside mobile devices are the ARM architecture. That's using Cortex, and that's often seen in Android, Ubuntu, iPhones, iPads and so on, and it can also run Windows 8 and Windows 10. The other type, the more traditional type, has grown up around the PC, and that's x86 type architecture, and then on to x64 architecture, 64-bit or 32-bit. And for this we see different processors for that. i7 is a typical processor here that we get, i5, i3, i7 and so on. And most of the major operating systems run on this type of architecture. Windows 7, Windows 8, Mac OS and so on, all run around the standard Little Endian type format operating architecture. And this is what we see in terms of the evolution. So we actually find that the Intel processors have typically focused on high performance and not with very little care of the actual power dissipation or the power utilization. Often they're very fast, have lots of cache memory and so on, lots of cores. This though doesn't quite work in terms of mobile devices or embedded devices, as they can be too power hungry. So the ARM architecture has typically started around more low power devices which take much less power than the high level ones, such as the Xeon processor here. So as we've moved up, a typical one that we see now is the ARM Cortex A15, which is used on many Android devices. It's a fairly fast processor, up to 2.5 gigahertz with up to 4 cores. Not too much in the way of cache memory. As we can see, this has a much larger area of cache built into the actual processor. So i3, i5 and i7 are all typically focused on desktop type computers, where these ones down here are more focused on mobile devices and embedded devices. Okay, so this is basically how it works. We have a microprocessor and we have some memory. Basically what happens is that we have the fetch execute cycle. The processor has a number of instructions that it goes through sequentially, and then it wants to access an area of memory, put the address on the address bus, and then pull the data across from there, does some processing, and then wants to write back. It then creates a write, puts the address it wants to put back into memory, and then we'll put the results back into the memory. The processor it has a number of registers that it uses, almost like scratch areas, and it loads up things into the registers and then does operations on them, and will load the results back into the memory. We have increasingly we have a number of cores within inside the processor itself, and that allows for parallel operations. So in this case, our 2 core could run 2 different systems at the same time. Or we can have a quad core, or a hexacore, or even an octa-core, such as in a Xeon. In this case, we have 8 cores. Each could be running their own processes or even their own operating systems. And it's up to the operating system itself to be able to isolate each of these instances and to make sure that they can all run in parallel. Okay, so if you're interested, this is what our x86 architecture looks like. We have a north bridge and a south bridge. The north bridge is for very fast operations into memory, back and forward. This has to be very fast. Typical bus speed about 800 meg here. Processor running about 3 gig. Okay, so we slow down automatically when we come out into this part here. And then we slow down even more when we go out to the slower devices such as the keyboard, the mouse, and other old legacy type buses here. Okay, the processor itself typically has an onboard cache, because what it wants to do is it wants to run as fast as possible. This is typically run at 3 gig, where this might only be running about 800 meg here. So we're going to slow down. So the onboard chip, the onboard cache, tries to make a guess as to what's going to be required from the memory next. So it will try to load up into this first level cache as much as possible the data that's required. So when the microprocessor asks for the memory, hopefully it will go to the local cache to be able to take the data from there. So the cache controller is continually trying to make a guess and then taking the memory that it has from the main memory or from the second level cache in this case, and trying to load it up into the processor, and most of the time it gets it right. When we see the processor itself now, you can see the cores here. I can see a great deal of memory is actually taken up through the cache area of memory. The memory area looks fairly consistent in the layout here because it's just a whole bunch of transistors. You can see areas of memory within inside the processor itself, such as these ones, all different levels of caches within inside here. You can even have a graphics processor built into the processor itself. Okay, so that's what processor architecture looks like. Now let's look at our IP camera. Okay, so this is the camera that we're going to use here, and we'll see how we can actually access it. Okay, so there's the camera there, and what we have is typically an Ethernet type connection. So the Ethernet connection allows us to be able to configure the device when it has no Wi-Fi connection. So the Ethernet connection will use DHCP, so if we connect it through a switch, say to a wireless router, then the wireless router acts as DHCP and we'll give it an IP address. We then have Wi-Fi so that we can contact it when we have no Ethernet connection. So what we'll find in this device, it uses a Ranklin MIPS 24K 4.1 12 800 and 384 megahertz. And it's running on a Linux version. Many embedded systems use embedded Linux, and this is the version that's actually using them. itself, it uses BusyBox to be able to create the core Linux. So this is an easy install. Basically, it's a single executable that goes onto the device, and it creates the core Linux system. We then have firmware, which comes along into the NVRAM, which is distributed typically through a bin file. So the bin file will relate to the version of the distribution that we require for the device. So we've really got to watch what we download here, because we could destroy the whole device if we don't watch. And what we'll find is that there is a telnet daemon running. So telnet allows us to be able to remotely log into the device and do various things, and also a web server. So the web server is running so that someone can connect over the web, over a web connection, and view the streaming video or the camera itself. Okay, so that's what we have there. So the first thing we'll do is that we'll get connected to the device. So it's out the box, nothing done to it, it's been reset. So when we connect to it, we'll find that this is the firmware. So probably the first thing we do is we go and have a search for that firmware, and it's fairly easy to find it. If we just find .bin, we'll be able to find that. So I'll let you have a look at the .bin file that we have for it. And it's there. Okay, so this is the bin file for it. It's the most up-to-date version for that camera, and we'll analyse that in a little minute. Okay, we also have a web interface version that we could also download, and we can update that. This is our MAC addresses. So what we'll do is that we'll get connected, and then we're going to run nmap to be able to see what the ports are that are open. We're going to try to see if we can get in through HTTP or Telnet, and then we'll use Hydra to be able to see if we can try to usernames and passwords. Of course, we shouldn't do this at all if it's not our equipment. Everything I'm doing is on a local private network. We're then going to run Kali binwalk. In binwalk, we'll be able to have a look at the distribution for the firmware. Then we'll extract that, and then we'll see if we can find any information around the default password, and we'll have a look at basic vulnerability for it. Okay, so what I've got is a very simple wireless access point. Okay, so it's just an old one that I have here. So I've connected in the Ethernet port to it for the camera. Okay, so let's have a look to see if we can actually find the camera. So we'll have a look at the attached devices, and we can see straight away, hopefully, that this is one of the MAC addresses there. So the device itself is connected at 192.168.192.168.2, and there it is there. Okay, so we have connectivity. So we'll just see if we can connect to it. Okay, so it's certainly there. Okay, so the first thing we'll do is we'll have a look at nmap to see if we can actually see which ports are actually open on it, and we can see that Telnet is open, HTTP and asterisk. So from here, what we're going to try to do is we're going to try to see if we can determine the HTTP password. So often what we'll do is see if we can log in. We'll try Telnet first. So we'll try admin and password. That doesn't work. Admin and pass, root, and pass. Okay, so what you'll see is that we're getting locked out in terms of the actual login for the system. So we obviously couldn't use something like Hydra to be able to get into the device from here. So the first thing we'll do is we'll actually have a look to see if we can get in. So obviously Telnet locks us out, but we'll have a look to see if we can get in through Hydra. So let's have a list of. So I've set up some usernames and some passwords. Okay, so let's go ahead and I just slow this down. Okay, so that's going to try from the usernames and also the passwords. So it's just gone through and trying each one in turn. And I've got a delay in between there just so you can actually see it going through each of the options. Okay, and it's found one there. So admin and 1, 2, 3, 4, 5, 6. And there we are. Okay, so here we are here. Okay, so we can move the camera around. Hopefully. There we go, there's the wireless router. Those will just place it up here. And there we go, we can move it up and down. And round. And it even does infrared. Hello. Okay, so that's set up there. Okay, so there's the details that we can see. Now we're into the camera. That's the firmware version, and so on. Okay, so Telnet will be more difficult, so we won't be able to use Hydra for that because it's obviously going to lock us out every 3 attempts. But you can see that the web didn't actually lock us out, so that's the problem with the Internet of Things, in that often they don't have a logout, they don't have a automatic lockout after a certain number of tries with a lockdown time. So what we'll do, we'll now have a look at our Kali instance. So got Kali running here. Okay, so we're now going to have a look at the standard firmware that comes with the camera. So this is the most up-to-date one. So you can see that's what the version was. So with that, we can actually have a look to see what's actually in the distribution. So if we have a look down, so one thing we can actually see is that there's the daemon. So the daemon is the process that runs, that makes the whole thing actually work. And we can see other things like there's a shell command to be able to run the actual camera. Okay, so often what happens is that we have a C++ program, it's then compiled, and a lot of the text that's actually inside the program, such as the messages, actually is not obfuscated, and we can actually view these things. So what we'll do is we'll extract the bin file. Just try and find. There. Okay, so I'm going to extract it from the bin file into an image file, to zip. Okay, and then what I'm going to do is unzip the image file. And so that's created the system as it was. So we'll have a look in the bin, and there's our daemon there. So what we'll do is we'll just list it, and then we'll have a look. Okay, so it looks all gobbledygook because that's the machine code, but you can actually see within it there's a whole lot of messages and things like that with inside there that can actually give some details away. So we can actually have a look through that and see if we can find something. And there's an interesting thing there. So we see here this here is the etc. is the password etc. file, or the contents of the password file. So we can copy that. Okay, and then what we can do is we can run John the Ripper. Just have a look at the options. Okay, so we'll just show that. And there it is there. Okay, so it's the same, it's actually the same, it's root and 1, 2, 3, 4, 5, 6 for the telnet connection. So what we'll do is that we'll just go ahead and we'll be able to telnet into the device now, hopefully. Root and 1, 2, 3, 4, 5, 6. There it is there. Okay, so this is us on the device now. So system, and here is the web site there. Okay, so so something like index. So there's the index.html file, which is actually loaded up whenever we access the camera. It's this one here. Okay, but we can go into go to the top. Go into proc, and we can actually have a look at the device. So there's the CPU, as we've seen. There's the processor there. It's a MIPS 24K. We can look at the actual mount. Okay, so that's how it's loaded into memory. We can actually have a look at our partition information in there. And there's a whole lot of other things that we can actually have a look at from there. We can have a look at our memory info. Okay, so that's how the memory is actually used. You can see there's not really that much memory actually on the device itself from there. Okay, so that's allowed us to be able to get into the device. just review what we did there. So the nmap allowed us to be able to discover the ports that were actually open on the device. And then using Hydra, we were able, there was no lockout on the login for the web. So it's a really bad thing not to have that on any sort of service that's exposed to the internet. From there we had to look at the firmware, and then take a walk through what was actually added onto it. We can see there's the daemon there that actually runs, and there are a few other things such as the IP camera shell that runs. Then from there we could actually find out some details of one of the accounts that we could use to log in through Telnet. Okay, so once we got in, then we could actually have a look around the system. Okay, so this has been a very simple example of accessing an Internet of Things device. So an important thing is that really security is a very important aspect of it, and then designers really need